This is session D4, spin 1 and other spin values, and also photon polarization. Last lecture was D3, where we did spin 1/2 particles and their spin states. Today we'll explore different spin values. Much of this lecture is optional, but you will need the material on plane polarization of photons for a future lecture. This lecture covers the different possible values for intrinsic spin angular momentum for elementary particles. We will simply call this spin. I'm uncertain about some of the material in this lecture, much more so than in previous lectures, so treat this as a guide that could be faulty. In quantum mechanics, for any particle, an electron, a proton, a nucleus, an atom, if you measure the angular momentum along any axis you choose in real three-dimensional space, the component of angular momentum in that direction of space is always an integer or half integer times h bar. It is quantized. A course in quantum mechanics would prove this. Angular momentum is the sum of orbital angular momentum of the spatial wave function and intrinsic spin angular momentum of the particle independent of its spatial wave function. This lecture covers intrinsic spin. We won't be interested in orbital angular momentum. Different particles are restricted to different sets of discrete values of the component of intrinsic spin angular momentum in a direction of space. For every subatomic particle or atomic system, there is a number called the spin of the system, for which we use variable s, which must be a non-negative integer or half integer. So 0, 1/2, 1, 3/2, 2, and so on. For a subatomic particle, the spin s is an immutable value for that particle. For an atom, there is a spin value for the atom's lowest ground state, but there are other values for excited states. For a system with spin value s, the component of intrinsic spin angular momentum measured along any particular axis, call it the plus z axis, will always have one of the following values. There'll be 2s plus 1 values between plus s h bar and minus s h bar. So s sub z will be one of the following times h bar. S minus 1, s minus 2, keep decrementing by 1 until we finally get to minus s. Note that the values in the list decrement by h bar, not by h bar over 2. However, for a particle with zero rest mass, such as a photon, so it's traveling at the speed of light, the direction of motion, call it plus z, is the only direction along which the component of intrinsic spin angular momentum can be measured, and it can only take on the two extremal values, plus or minus s h bar. So the spin of that massless particle is a two-state system, but it is not the spin 1/2 system. Particles with integer spin are called bosons. Particles with half odd integer spin are called fermions. Bosons and fermions behave differently in certain ways, some of which we will cover in later lectures. Each elementary particle, for example electron, has its own characteristic, intrinsic, immutable value of spin s and ratio of magnetic dipole moment magnitude in any direction divided by intrinsic spin angular momentum component magnitude in the same direction. For example, we found this ratio to be minus the g factor for the electron times the elementary charge E over twice the mass of the electron in SI units for the electron in lecture D1 on the sterngerlach experiment. These values are identical, universal for all instances of a given elementary particle, for example electron, in any possible experiment throughout the observable universe. Either or both of these characteristic quantities could be zero for some particular type of particle. The antiparticle of a particle has the same spin s as the particle, and the negative of the ratio above as the particle, as far as I know. This is a possible time to take a break. Let's do a table of different spin values. We'll look at spin values 0, 1/2, 1, 3/2, and 2. Now, the number of spin states is 2s plus 1. We said that before. So the number of states is 1 for spin 0, 2 for spin 1/2, 3 for spin 1, 4 for spin 3/2, and 5 for spin 2. Let's look at the actual spin states. For spin 0, the only spin state is 0 h bar. For spin 1/2, the spin states are plus or minus 1/2 h bar. We saw this in our last lecture, D3. For spin 1, the allowed spin states are plus 1, 0, and minus 1. This is for a particle that has mass. The photon is spin 1, but it has no mass, so it can have the spin states plus 1 and minus 1, but cannot have the spin state 0. A spin 3/2 particle can have spin states whose component spin angular momentum is plus 3/2, plus 1/2, minus 1/2, minus 3/2, and a spin 2 particle could have spin states of plus 2, plus 1, 0, minus 1, and minus 2. Now, for total angular momentum, we have seen, and we will use again, the operator s squared, total angular momentum squared, and it has eigenvalues of s plus 1 h bar squared. And for a spin 0 particle, that's 0. For a spin 1/2 particle, it's 3/4 h bar squared. For a spin 2 particle, it's 2 h bar squared, and so on. Now, the dimensionality of the spin state vector is the same as the value 2s plus 1, the number of spin states. So the dimensionality of the spin state vector is 1 for spin 0, 2 for spin 1/2, 3 for spin 1, and so on. And this is also the identical to the number of orthonormal basis vectors that we need to work on a problem. Now, at times we will need to use some spin state operator, which will be a matrix, and Its size for a spin 1/2 particle will be a 2x2 matrix. We saw that in the last lecture, D3. For a spin 1 particle with mass, it will be a 3x3 matrix. For a spin 3/2 particle, it'll be a 4x4 matrix, and so on. Now, let's list some example elementary particles of different spins. The only elementary particle that is spin 0 is the Higgs boson. But there are a lot of elementary particles that are spin 1/2. All leptons, which includes all electrons and all neutrinos, are spin 1/2. And all quarks are spin 1/2. Spin 1 particles include photons, gluons, the Z particle, and the W plus and minus particle. The Z and W plus and minus particles have mass, but the photons and gluons are massless. As far as I know, so far no elementary particle is known to have spin 3/2. Gravitons, if they exist, are believed that they will have spin 2. Gravitons are expected to be massless if they exist. Now let's look at some composite particles that include quarks, and so they are hadrons. Protons and neutrons we're familiar with. Those are spin 1/2 particles. We're less familiar or not familiar at all with pions, or also called pi mesons, but they have spin 0. And there are other hadrons that have spin 1 and spin 3/2. These are unstable particles. The proton is stable. Neutron is stable when it's in a nucleus with the proton. Now, all of the values of spin that are integral, those are bosons. So a spin 0 particle is a boson, and you might see the phrase scalar boson to mean that it's a spin 0 boson. Particles with spin 1 are called bosons. I mean, they are bosons, but they are sometimes called vector bosons or gauge bosons. And particles with spin 2 are bosons, and the graviton is sometimes called a tensor boson. Particles with spin 1/2 and 3/2, they are fermions. Now, is there a one-to-one mapping between spatial directions and normalized state vectors in the abstract spin space? Yes, there is for spin 1/2, but no for other values of spin. Now, what is the spatial angle between basis vectors? For spin 1/2, it's 180 degrees. So we can have a basis vector of z plus and z minus. They are 180 degrees apart, 180 degrees between basis vectors. But for spin 1 and above, it's a more complicated question, and so I haven't put anything in those boxes. It's not a simple angle. Now, what if we have a state vector and we rotate space along some direction, we rotate space by some number of degrees. That changes the state vector. How many degrees of rotation of space do we need to rotate back to get the identical state vector we started with? Now for spin 0, it's not applicable. Any rotation leaves the state vector unchanged. The state vector does nothing because there's spin 0 anyway. So no rotation would change anything. Now here's an odd thing. For the spin 1/2 system, you have to rotate space by 720 degrees, or 2 times 360 degrees, to get back to the original state vector. We haven't covered change of basis or rotation of basis enough to be able to show this, so I'm just telling you that it is true. For a spin 1 particle, if you rotate space by 360 degrees, you get back the identical state vector. For a spin 3 particle, I believe you rotate space by 240 degrees, but I couldn't find that listed in a book. And for a spin 2 particle, if you rotate space by 180 degrees, you get back the original state. So, what is the effect on a state vector of doing a 360 degree spatial rotation? There's no change for a particle with spin 0, 1, or 2. For a spin 1/2 particle, the state vector gets negated. Now, simply negating a state vector does not change any probabilities or expectation values, but the state does get negated. I believe a spin 3/2 particle its state would get negated also, but again, I couldn't find that in a book. Now, we looked at some elementary particles and composite particles that had different spins, but larger systems have spins also. Net spin, total spin. Let's take some example atoms that are in their ground state for total angular momentum. A hydrogen atom, its ground state and total angular momentum, including the nuclear spin, is spin 0. So is a helium-4 atom. Now for silver, the electronic total angular momentum is spin 1/2. That does not include nuclear spin. One reference I have says that the arsenic atom is spin 3/2, but for electronic total angular momentum. Now molecules also have net angular momentum. It's more complicated because not only do you have the electron spin and the orbitals, the molecular orbitals that the electrons are in, but you also have nuclear spin. So here I'm giving you what I believe is the ground state electronic angular momentum, not including the nuclei. So hydrogen H2 and nitrogen N2, I believe, are spin 0 molecules. Oxygen is a little funny. O2 has an electronic angular momentum of 1, spin 1, and this is called triplet oxygen. This is a possible time to take a break. Now photons and gluons are massless spin 1 particles, so they can only have spin component plus or minus h bar, and then only along the direction of their motion. Gravitons, if they existed, are expected to be massless spin 2 particles, so they could only have spin component plus or minus 2 h bar only along their direction of motion. Now here's a chart showing different elementary and composite particles, and not their spin value, but whether they're bosons under the red curve or fermions under the blue curve, and all hadrons are under the green curve. There's only one type of photon, and photons do not interact with one another. However, there's multiple types of gluons, and they do interact with one another. The force carriers of the fundamental forces are always bosons, but not all bosons are force carriers. Gravitons, massless if they exist, would be the force carriers for gravitational attraction. Photons, massless, are the force carriers for electromagnetic forces. Gluons, massless, are the force carriers for the strong nuclear force. Z and W plus or minus particles, each of which has mass, they convey the weak interaction, sometimes called the weak nuclear force. Now, pions or pi mesons, you will sometimes see them referred to as force carriers for the remnant strong nuclear force between protons and neutrons, but this is not the fundamental strong nuclear force conveyed by gluons that binds quarks together into composite particles like the proton, the neutron, and pions. Higgs bosons and the Higgs field give electrons and the Z and W plus or minus particles their masses. We won't be talking about Higgs further. Mesons, unstable composite particles composed of one quark and one antiquark, they're always bosons with spin 0 or 1. Baryons, stable or unstable composite particles composed of 3 quarks or antiquarks, they're always fermions with spin of 1/2 or 3/2. This is a possible time to take a break. S squared and spin spheres. In the last lecture, D3, we looked at the spin sphere for spin 1/2. We said that if we take that there's a total angular momentum vector, and if we dot product it with itself, we end up with the square of the operator S sub x along the x direction plus the square of the operator S sub y along the y direction plus the square of the operator z, sz, along the z direction. And it turns out that when you sum those together, you get the identity matrix times a factor of s times s plus 1 h bar squared, where s is the spin of the system. In the last lecture, we only did spin 1/2. Now, I'm not going to show this sphere as a 3-dimensional object, but what we're going to do is we're going to look at how the xz plane intersects that sphere. So this blue circle is the spin 1/2 sphere, but we're only looking at the portion of it that's in the xz plane. Horizontal is the x direction, vertical is the z direction. This is a spin 1. The blue system is a spin 1/2. It has two states for projection or component. So if we take the component along the z-axis, we get a spin value of plus 1/2 or minus 1/2, which I'm showing as these horizontal bars. But actually, that's not a bar in the plane. What it is a circle. It's the intersection of the plane, z equal plus 1/2, with the sphere. So it's a circle in the perpendicular plane, and the intersection of the plane z equals minus 1/2 with the sphere. So that is a circle in the perpendicular plane. But visually, we can see that there are two component spins, plus 1/2 and minus 1/2. For spin 1, we get this green system. A larger sphere, 3 states, plus 1, 0, minus 1. Notice the difference between the spin states. 1/2 minus 1/2 is 1 h bar. So the spacing between these two states is 1 h bar. The spacing between these states is 1 h bar and 1 h bar. Now the red case is spin 3/2. A larger sphere, 4 states, 3/2, 1/2, minus 1/2, minus 3/2. And spin 2 has 5 states, 5 component projections, SZ, plus 2, plus 1, 0, minus 1, and minus 2. Now when we measure SZ, it is quantized, but then SX and SY are indeterminate. So we shouldn't really say that the spin points in some direction. We should use more careful wording to say what direction we're measuring the spin component along. When we've measured a definite eigenvalue of SZ, the angular momentum vector presumably could point anywhere along that circle, but we cannot say it points in any particular direction in real physical space. We can only identify the component projection that we measured. The component's projections along other directions in space are uncertain. Nevertheless, it's just too easy to say that the spin points in the z direction, and I'm sure I have said that on occasion, and books will say that on occasion, but really we don't mean that the spin points in that direction. We mean that we measured the spin along that direction. This is a possible time to take a break. Spin 1 particles with mass. A beam of spin 1 particles with mass and 0 electrical charge and 0 orbital angular momentum, if we put those in a sterngerlach experiment, they should split into 3 beams. However, this is easier to conceive abstractly than to find a real example that would split into 3 beams and where someone's actually done the experiment. So it's more of a thought experiment. We cannot use photons or gluons. They are spin 1 particles, but they have 0 mass, they're not affected by the magnetic field, and gluons are not isolated free particles. We cannot use Z or W plus or minus bosons. They're spin 1 particles, but their lifetime is less than 10 to the minus 24 seconds. W plus and minus are electrically charged, and Z is not affected by the magnetic field. I could not find whether any neutral atoms have been used in a sterngerlach experiment and split into 3 beams. A neutral atom might have a total angular momentum of 1 if it has a single unpaired electron and that electron is in an s orbital, so 0 angular momentum, if the total angular momentum of the nucleus is spin 3/2. If this produces a ground state with total spin 1. Similarly, a neutral atom might have a total angular momentum of 1 if it has a single unpaired electron and that electron is in a p orbital with orbital angular momentum component of plus or minus 1. If the total angular momentum of the nucleus is spin 1/2, and if this combined produces a ground state with total spin 1, but the high magnetic field required for the sterngerlach experiment decouples the spin contribution from the nucleus from the contribution from the electrons, I believe. So actually neither of those cases would produce a spin 1 particle that would give 3 levels in a sterngerlach experiment. It turns out, I believe, that the ground state of the oxygen molecule, O2, is spin 1. The electronic contribution from orbital angular momentum and electron spin, not including nuclear spin. Because the molecule has 2 unpaired electrons in 2 different molecular orbitals. The antibonding pi x star and pi y star molecular orbitals. Hund's rules, the quantum mechanics of which I don't yet understand, say that the 2 electron spins will be parallel in the ground state. This state is called triplet oxygen. As far as I could tell, these molecules should split into 3 beams in a sterngerlach experiment, but I don't know whether this has ever been tested or demonstrated. This is a possible time to take a break. For a spin 1 particle with mass, we must choose 3 independent, non-overlapping physical basis states. 3 physical basis states selected for the particular physics of that system. The choice of basis states is not unique. Say we will measure the z component of intrinsic spin angular momentum. The plus z direction in real physical space will be the direction for the z plus physical basis state, whose SZ eigenvalue will be plus h bar, spin 1. The minus z direction in real physical space will be the direction for the z minus physical basis state, whose SZ eigenvalue will be minus h bar, again, spin 1. There must also be a physical basis state whose SZ eigenvalue will be 0 h bar. As far as I understand it, any direction in the xy plane perpendicular to the z-axis would serve as a possible physical basis state for eigenvalue 0 h bar. I believe that nothing in the choice of z direction for spin 1 determines a unique single direction for that 0 h bar physical basis vector. We could choose the plus x axis if we wish. The 3 physical basis states are physically orthogonal for a spin 1 particle with mass. There's none of one basis vector in the other. There's 0 projection. This is a matter of physics for our choice of the basis vectors. Unlike for spin 1/2, for spin 1 it's no longer true that every state vector of the abstract vector state space must be an eigenvector of the component of spin in some direction of real physical space. The pure states of a spin 1 system need not be associated with a spin eigenvalue in any spatial direction. This is more complicated and confusing than spin 1, but we're not going to get into this complication. This is a possible time to take a break. The main reason that we spend time considering spin 1 is because the photon has spin 1. Photons are spin 1 elementary particles, so they are bosons. Photons are the force carrier for electromagnetism, electric and magnetic fields. Photons have zero rest mass, and so in vacuum, photons travel at the universal constant speed of light in vacuum, c. The zero rest mass of the photon gives the electrostatic force unlimited range, falling as 1 over r squared. A spin 1 particle can have component of spin along some direction equal to plus 1 h bar, 0 h bar, or minus 1 h bar if the particle has mass. But photons have zero rest mass, and so the photon spin state can only take on the two extremal values of directional component of spin, plus 1 h bar or minus 1 h bar, and then only along the photon's direction of motion. Therefore, the spin states for the photon are a two-state system, but they are not the spin 1/2 system. We cannot use a sterngerlach machine to separate the spins of photons. Photons do not have electrical charge or magnetic dipole moment. Magnetic fields do not change the trajectory of photons. It's photons that communicate or propagate electromagnetic fields. Helicity. A particle with a positive or negative projection of its intrinsic spin angular momentum along its direction of motion is said to have positive, also known as right-handed, or negative, also known as left-handed, helicity. And we need this for the photon. This is a possible time to take a break. Photon circular polarization. I'm not 100% confident on this material, so bear with me. I've checked it multiple times, but I'm not expert in this. So circular polarization is confusing. We need it in order to get to plane polarization, which will be easier, in fact easy. So we need circular polarization to get to plane polarization. A photon with a spin component projection of plus h bar in the direction of its motion has positive right-handed helicity and is said to be right-handed circularly polarized or right circularly polarized. A photon with a spin component projection of minus h bar in the direction of its motion has negative or left-handed helicity and is said to be left-handed circular polarized or left circularly polarized. Now, there are two conventions for handedness of light. Quantum mechanics uses the handedness convention from the point of view of the source, not the receiver. So my diagrams in this lecture are for that convention and might differ from a book that you could pick up on classical optics, which uses the handedness from the receiver. And different websites like the page on Wikipedia show both conventions. Hopefully I have not made any mistakes, but don't get frustrated. The convention is not that important for our purposes. Our purpose is to get to plane polarization, which will be easy. Now, let's take a photon which is traveling in the plus z direction, which is out of the page toward us. And we'll look at the xy plane at z equals 0 at some time t. We have two different circularly polarized electromagnetic waves. The one on the left, in blue, is the right-handed circular polarized photon. The one on the right, on red, is the left-handed circular polarization. This graphic shows the rotation of the electric field direction in the xy plane, z equals 0, at time t for those two circularly polarized electromagnetic waves. You can think of them as electromagnetic waves. Photon behaves the same, but you will find more diagrams of polarization of electromagnetic waves than photons, so think of it that way. We use the handedness convention from the point of view of the source. So in this case, the wave is propagating toward us, so the source is on the other side of the page. Let angle phi be positive when it's counterclockwise from the x-axis toward the y-axis. So for our right-handed circular polarization, the direction of the electromagnetic field at z equals 0, it rotates with time, with the angle being omega times time. So it's rotating in this counterclockwise direction. That's called right-handed circular polarization, because if you were to take your right hand and you put your fingers along the circle in the direction that the electric field vector is rotating, your thumb will point toward you, so away from the source. Left-handed circular polarization is the negative, that the electric field vector is rotating clockwise with time. And so if you put the fingers of your left hand along this circle, your thumb will point toward you, away from the source. Right-handed circular polarization is also called clockwise circular polarization, because in that convention, you're looking away from the source. So what I said is counterclockwise, looking toward the source. If we were at the source looking away, we would call this clockwise. And that's the convention. I know it's confusing. Left-handed circular polarization is called counterclockwise circular polarization, but we're not going to use those terms anyway. But you will see them if you look at Wikipedia or some book. This is a possible time to take a break. Now, following is a graphic from Dave3457 on Wikipedia showing the direction of the electric field vector at different points z along the direction of motion of the wave, but at a single time for our right-handed circularly polarized electromagnetic wave propagating to the right. you see that the tip of the electric field vector forms a helix in space, and that helix moves in the plus z direction in time, but we're just showing a single time here. The arrows are the direction vectors at different plus z values at a single time. The electric field has a constant magnitude everywhere in space, while its direction steadily changes in a rotary manner. Not shown, the magnetic field vector is at a right angle to the electric field vector and to the z-axis, and proportional in magnitude to it. It would be too complicated to show them both. It's sufficient to show one. Now, if this is confusing, don't worry about it. We're soon going to switch to plane polarization, which is very easy. Here's a different representation. This representation shows the x and y components of the electric field at the different z values at one time. Again, for our right-handed circularly polarized wave. Here, the blue sine wave is in the xz plane, and the green sine wave is in the yz plane. And notice that they are 90 degrees out of phase. When one has a maximum value of plus or minus 1, the other one has value 0. They are out of phase. Now, following are comparable graphics for the case of a left-handed circularly polarized electromagnetic wave. Right circular polarization, spin projection plus h bar, and left circular polarization, spin projection minus h bar, those are orthogonal physical states for a single photon. Each state has zero projection to the other state, and these are eigenstates of S sub z. You can buy circular polarizing filters inexpensively. Say we orient the plus z axis to the right and orient a circular polarizing filter in the xy plane to pass right circularly polarized photons traveling left to right in the plus z direction. When it passes right circularly polarized photons, it blocks left circularly polarized photons traveling left to right. Now, I believe if you flip that polarizer 180 degrees along the x-axis or the y-axis, that would cause it to now block right circularly polarized photons traveling left to right and pass left circularly polarized photons traveling left to right. If we place two circular polarizers with opposite orientation, we will pass little or no light through the pair. We can treat a photon or light generally traveling in a direction, plus z, as a two-state system, with the two orthonormal basis states being right circular polarization, ket R, and left circular polarization, ket L. And the inner product between them will be 0. They're orthogonal. For photons, we can express the intrinsic spin angular momentum component operator Sz as plus h bar times the projection for right circular polarization, ket R bra R, minus h bar projection for the left circular polarization, ket L bra L. Now that was all pretty complicated, but now we will simplify. This is a possible time to take a break. Photon plane polarization. The spin, helicity, and circular polarization of a photon or light generally traveling in a direction plus z can be and often is usefully re-expressed in terms of plane or linear polarization states, even though these will not be eigenstates of spin Sz. Following is a graphic from author P. Wormer of a vertically polarized electromagnetic wave at a moment in time. And this graphic is unchanged from that Wikimedia website. So this is plane polarized. The electric field is shown in red, and it always points parallel or anti-parallel to the x-axis. This e-axis is the x-axis. So it's not rotating. This is a snapshot in time. The wave is traveling left to right, but we don't see that in the snapshot. So at this snapshot in time of all space, the electric field is this red sine wave in space, pointing in the direction plus or minus x. The magnetic field B in the y direction is in phase with the electric field. It's also moving left to right, which we don't see, but it points in the plus or minus y direction. This state is vertically polarized because the electric field is in the direction plus or minus x. Let's call this state ket V for vertical plane linear polarization of the electric field, parallel to or anti-parallel to the x-axis in the vertical xz plane. Let's call ket H a state of plane linear polarization of the electric field parallel to the y-axis in the perpendicular horizontal plane, the yz plane. So not this diagram, but if we rotated this diagram 90 degrees, so the electric field was along the x direction and the magnetic field was along the y direction, that plane polarization we would call ket H. Now, ket H and ket V form an orthonormal basis, their inner product is 0, for plane polarization states. This is a two-state system. This is different than, but not independent of, the circular polarization basis states for describing circular polarization, helicity or spin of a photon. But photon spin is a two-state system, so we can relate the two non-independent basis systems to one another. And they relate as follows. Right circular polarization ket R is 1 over square root of 2 times vertical polarization ket V plus I times horizontal polarization ket H. Left polarization replaces plus I with minus I. If we take right plus left, we find that vertical polarization is 1 over square root of 2 times right plus left, and horizontal polarization is minus I over square root of 2, right minus left. So they relate to one another. If we have one, we can get the other. In lecture D3 on spin 1/2 particles, we discussed using 1, 2, or 3 linear plane polarizers on a light beam. We used this as an example, even though we were talking about spin 1/2 in that lecture. And I showed this diagram. The polarizer frame in the back is vertical polarizing, the frame in the front is horizontal polarizing, and the frame in the middle is oriented at 45 degrees. In a future lecture, we will cover an entangled state of 2 photons, and there we will use plane polarization basis states, not circular polarization, helicity, or spin. Now, a photon's spin or polarization state can be any superposition of its basis states, which leads to elliptical polarization or plane polarization at any angle from the x-axis. Photon polarization corresponds exactly to polarization of electromagnetic fields in classical electromagnetism. The three basis states for a spin 1 particle with mass do not correspond to the spatial directions x, y, and z, which are 90 degrees apart. However, for massless photons traveling in the plus z direction, we are able to call the vertical and horizontal polarization directions, the x and y axes, 90 degrees apart from one another and from the direction of travel plus z. This is a possible time to take a break. Unpolarized light. Light is said to be unpolarized when the ensemble of photons have more than one polarization state, typically randomly distributed polarizations. The light from the sun is unpolarized. Photon emission from an atom. Total angular momentum is conserved in quantum mechanics as well as classical mechanics. When an electron in an excited state of an atom de-excites to a lower energy level and a photon is emitted, total angular momentum is conserved, and the photon has some angular momentum. However, things may be complicated because the initial and final states could differ in orbital angular momentum of the electron, or the spin direction of the electron, and the photon has spin, and the emission of the photon can also involve orbital angular momentum relative to the center of mass of the system. Way too complicated for us to cover, but certainly the spin of the photon is involved. Now here's a link to an article about how spins relate to the laws of the universe. This might interest some learners. I understand most of it, but not all of it. So I'm giving you this link for learners who want to see what the article says. It's not required for my lectures. This is a possible time to take a break. Now the remainder of this lecture is optional, but it will interest some learners. Neutrinos. Neutrinos and antineutrinos are elementary particle fermions with spin 1/2. Neutrinos are electrically neutral and only interact via the weak interaction, also known as the weak nuclear force, whose range is smaller than the size of a proton, and gravity, though this has not been experimentally verified. The masses of neutrinos are much smaller than the electron or other elementary particles with mass. It's like 1,000,000 times smaller than an electron. Neutrinos generally travel at near the speed of light because their mass is so light, and they're typically emitted with higher kinetic energy than their rest mass energy. So neutrinos are generally relativistic, and we can't use the Schrödinger equation for their spatial wave functions. But we can treat their spins just as we treated electrons. Neutrinos have some very unusual, unique properties compared to other elementary particles. One of these properties is that matter neutrinos seem to only ever have left-handed helicity. They are left circularly polarized. Their spin angular momentum is in the opposite direction as their motion, so minus h bar over 2. And antineutrinos only ever have right-handed helicity, right circularly polarized. Their spin angular momentum is in the same direction as their motion. plus h bar over 2. Neutrinos have non-zero rest mass, but their spin cannot point in an arbitrary direction in space. It can only point along their direction of motion. And unlike massless particles, neutrino spin is a one-state system, not a two-state system. This is a possible time to take a break. Over 100 trillion neutrinos from the Sun pass straight through your body without interaction every second of your life. Neutrinos and antineutrinos interact with other matter particles only extremely weakly. Neutrinos are emitted by nuclear fusion in the hot, dense core of the Sun. Once emitted, they pass through the layers of the Sun without interaction or delay at nearly the speed of light, greater than 0.99999999 times the speed of light. Some of those neutrinos arrive at the Earth 8.5 minutes after they were emitted in the core of the Sun. They pass straight through the Earth. There also are neutrinos coming from every other star undergoing nuclear fusion in the galaxy and in the universe. Neutrinos are also emitted by supernova explosions. Neutrinos were emitted in the first seconds and minutes after the Big Bang, and almost all of those neutrinos are still traveling the universe at nearly the speed of light, having not yet interacted with matter over 13 billion years. Neutrinos and antineutrinos are also emitted in some nuclear radioactive decays, in beta decays, and from nuclear reactors. The highest energy ever detected for a cosmic neutrino so far is about 2 × 10⁻⁵ electron volts. This is like 5 billion times higher energy than the typical neutrino from the Sun. This is a possible time to take a break. Let's use one of the nuclear fusion processes in the hot, dense core of the Sun as an example of particle spins and conservation of angular momentum, even though we have not covered some material such as addition of angular momentum and some particle conservation laws. And I'm not an expert on this, so bear with me, but I think some learners will find this an interesting example. Our Sun converts hydrogen to helium in its hot, dense core, primarily via the proton-proton chain reaction, the first and slowest step of which is to fuse 2 protons into a deuteron, a deuterium nucleus, 1 proton and 1 neutron bound together. And in the process, they emit a beta plus particle, a positively charged positron, which is the antiparticle to an electron, and a neutrino with 100 to 400 kilo electron volts of kinetic energy, which makes it very relativistic. So the equation for this conversion is proton plus proton becomes 1 deuteron, which is a proton plus a neutron, plus a beta plus particle, plus a neutrino, an electron-flavored neutrino. Protons are constantly whacking one another in the core of the Sun, yet this reaction is extremely slow, extremely low probability. The average proton in the core of the Sun It's constantly whacking other protons, but it takes 9 billion years on average before it successfully fuses with another proton, which is why the Sun has a lifetime of billions of years. Once these two protons have fused, it only takes another 400 years to produce helium-4, which will not fuse any further in the core of our Sun. The equation above, which I'm repeating here, it conserves electrical charge, as it must. The left side has electrical charge of +2. This deuteron has charge +1. This positron has charge +1. Neutrino is neutral. It conserves baryon number. There were 2 baryons on the left side. There are 2 baryons in the deuteron on the right side. The positron and neutrino are not baryons. It conserves lepton number. There were no leptons on the left side. There's no leptons in the deuteron. The lepton number for the positron is -1, and the lepton number for the neutrino is +1, so it conserves lepton number. But the reason why we want to use this example is to see what happens with spin. There's no orbital angular momentum in this case, so we'll only be dealing with spin angular momentum. The protons, the neutron, the positron, and the neutrino, they're all spin 1/2 particles. In a future lecture, probably the next lecture, we will cover how spins combine for pairs of particles. But a pair of spin 1/2 particles together, they can have either combined spin of 1 or 0. The ground state of the deuterium nucleus is spin 1, I believe, which I think we will cover in the next lecture. In our example, let's take the 2 protons to have had combined spin of 0 before the fusion, the deuteron to have spin component of +1, and the positron and neutrino together to have combined spin of 1 and spin component of -1 when they're emitted. I'm just making this choice so that we have something concrete to look at. Let's look at this reaction one layer deeper and focus on the proton that converts to a neutron. So the proton converts to a neutron by emitting a W+ particle, and the W+ particle decays into a positron plus a neutrino. So we end up with the proton turning into a neutron plus a positron plus a neutrino. In the process, the proton flips its spin and emits a virtual positively charged W+ particle, which is a spin 1 particle, as the proton turns into a neutron. I'm going to give an example listing the spin of each particle and its z component of spin as a pair within parentheses, and the particle as a subscript. And this is just an example. I'm going to take z to be the direction of travel of the emitted neutrino. So the proton is a spin 1/2 particle, and I'm saying that this proton started out with a spin component in the z direction of -1/2. It emitted a W+ particle, which is a spin 1 particle, and in this case it had spin of -1 h-bar in the z direction. The proton became a neutron, which is a spin 1/2 particle, but its spin is flipped relative to the proton. So the proton started out spin -1/2, the neutron became spin 1/2, and the W plus particle took away minus 1/2 h bar in the z direction. And then the W plus particle decayed into a positron, which is spin 1/2 particle, and in this case, along the z direction, it had spin angular momentum of minus h bar over 2, and a neutrino, which is a spin 1/2 particle, and it took away minus 1/2 h bar in the z direction. In all steps, the z component of spin summed to minus 1/2. We started out with minus 1/2. Here we have plus 1/2 minus 1. And here we have plus 1/2 minus 1/2 minus 1/2. So it always summed to minus 1/2 for the z component of spin. Each step also is combined spin 1/2, but this requires additional material and complication that we're not going to cover, so we'll just leave that as is. This is a possible time to take a break. Now we can look at this at an additional level of depth as well to see what's happening here. The proton consists of 2 up quarks, each with electrical charge of plus 2/3 e, and a down quark with electrical charge minus 1/3 e. When we sum them together, the proton has charge plus e. The proton also has a sea of gluons, and we can ignore those completely here. So the proton consists of up, up, down in terms of quarks. The neutron consists of 1 up quark and 2 down quarks, up, down, down, which gives it a total electrical charge of 0. Now each quark is spin 1/2. 3 spin 1/2 particles together can have combined spin of either 3/2 or 1/2. But the proton and neutron, they are always combined spin 1/2. They are never spin 3/2. One of the quarks always has spin opposite to the 2 others. It doesn't matter which. Let's start with a concrete example with the following up, up, down quark description of a proton with spin z minus, so minus 1/2 h bar. So the proton consists of 3 quarks, an up, and a down, and I'm saying that their z components of spin are minus 1/2, plus 1/2, which sum together to be minus 1/2 of the original proton. Now the up quark that I'm showing in the middle, I'm saying that it's the one that will emit a positively charged W particle, and that will change it from an up quark to a down quark, and also flip its spin from z minus to z plus as follows. The first up quark is unchanged, the third down quark is unchanged, but the middle quark, this up quark, it changed to a down quark, it flipped its spin, and it emitted a W plus particle. The z component of spin here is plus 1/2 minus 1, or minus 1/2. The z component of spin angular momentum is unchanged. It's conserved. Now, almost every time the W particle gets emitted, it's immediately absorbed by the other original down quark, the one on the right, which I'm showing as the third quark. This W plus gets absorbed by this down quark, and it changes it to an up quark, and flips its spin from plus 1/2 to minus 1/2. So we get the following. Now notice, this is identical to the original proton, it's just written in a different order. The original proton was an up quark of minus 1/2, an up quark of minus 1/2, and a down quark of plus 1/2. So when that W plus particle gets absorbed by the down quark in the same proton, there's no external evidence that anything happened. The proton is unchanged. And that's what happens almost all the time when that W plus particle gets emitted. However, if this proton is in intimate contact with another proton at the time the W plus is emitted, there is an extremely small probability that the W plus will decay instead of being absorbed by the down quark. In this case, the proton has become the following neutron. And the neutron and the proton remain bound as a deuteron. Nuclear fusion has occurred and energy was released by the W plus particle decaying. So here is the original up quark, here is the original down quark, but the middle up quark changed to a down quark of spin 1/2. The W particle went away and it decayed, and we're not showing it in this line. But this is an up, down, down, so it's a neutron. And the sum of the z components of spin is minus 1/2 plus 1/2 plus 1/2 is plus 1/2. So this is a perfectly fine description of the neutron that the proton turned into. Although these different views of this process are complicated and I've oversimplified them and I've skipped important material, I hope these give you some examples of conservation of angular momentum and how to deal with spin 1/2 and spin 1 particles. This is the end of lecture D4.